Okay, hello everyone. We're gonna finish up the argument from class today. What was the argument from class today? Well, it took us the whole hour and we still kind of didn't finish. We kind of finished. What we did in class is introduce this thing called a Hamiltonian cycle, which is a cycle in a graph which visits every vertex exactly once. Built into the definition of cycle is that vertices are visited at most once, but a Hamiltonian cycle visits every vertex. And we did an example of a Hamiltonian cycle on the dodecahedral graph. Okay, we then proposed this theorem or conjecture, which we intend to prove, that if there are enough edges in a graph with n vertices, then there must be a Hamiltonian cycle. And in period 9, I thought this was a kind of a pretty picture that we made, where we said, okay, look, of course, a disconnected graph is not going to have a disconnected graphs are not going to have Hamiltonian cycles, because you certainly can't visit every single vertex on a walk. Because there just doesn't even exist a walk between some vertices. That's the definition of disconnected. On the other hand, a complete graph obviously has a Hamiltonian cycle. You just do whatever you want. Every single vertex is connected to every single vertex, so pick any permutation whatsoever of the n vertices and simply visit them in that order. You're never missing an edge between a vertex and another vertex because the graph is complete. So if a complete graph definitely and obviously has a Hamiltonian cycle. In fact, it has a lot of Hamiltonian cycles. There's a distinct Hamiltonian cycle for every permutation of the vertices of that graph. And a disconnected graph obviously doesn't. Then at what point does a graph have a Hamiltonian cycle? Maybe here or something we cross the line from disconnected to connected by adding more and more edges. Is it true that every connected graph has a Hamiltonian cycle? Well, certainly not, because there are some graphs that don't even have a cycle at all, say this graph. Okay, and yeah, at what point are there enough edges that we can say there's a Hamiltonian cycle? Well, it's a little bit unclear, and there's not a simple, obvious property which I can state, which explicitly will tell me exactly when I will have a Hamiltonian cycle and when not. But this theorem says, hey, if every vertex has degree at least n over 2, then there is a Hamiltonian cycle. So I defined this thing delta to be the degree of the minimum degree vertex. It's the number of friends of the person with the least number of friends. And okay, then we went in to try to prove this theorem. The first thing we did was to take care of a little technical side issue, which in fact is a kind of a theorem in its own right, which is of some level of difficulty, not to understand, but to prove that in fact this sufficient condition, that delta is greater than or equal to n over 2, that everyone has at least n over 2 friends, everyone is friends with at least half the people, that is sufficient to show that the graph is connected. And we did a little argument, which I won't go into the details of, by contradiction, by supposing that the graph is disconnected. If the graph is disconnected, then there just simply aren't enough edges in these two components to meet this condition that everyone be friends with half the people. Okay, finally we started the proof properly by taking a particular n and constructing the set of all graphs which meet the condition that delta is greater than or equal to n over 2, so that everyone is friends with at least half of the vertices, but there is no Hamiltonian cycle. This is the thing we want to show is impossible for a graph to meet this condition and yet not have a Hamiltonian cycle. Therefore, our conclusion is going to be that this set is in fact empty. And to prove that this set is empty, we're going to suppose that it's not empty. And if this set is not empty, then there are a lot of graphs in this set. How many? Well, okay, once you fix the number of vertices, then there are only a finite number of graphs that there can possibly be with a certain number of vertices. So this is in fact a finite set. And yeah, when you add all the edges, you get the complete graph. But if you add just some edges, you know, then you have fewer edges than the complete graph. So we defined, this was a key step, we defined this graph G to be the graph in this set with the most number of edges. So if there's any graph in this set if there's any graph in this set at all, by the way, there isn't, we're going to show, then there must be a biggest one, where we define biggest as having the most number of edges. And we state some facts about this graph G. Every vertex has degree greater than or equal to n over 2, but there's no Hamiltonian cycle. Also, by the lemma, this graph is connected. And, of course, since this is the graph in S sub n with the most number of edges that doesn't have a Hamiltonian cycle, then if we add just one edge to this graph, then we'll get a new graph which must have a Hamiltonian cycle. Because this is the biggest one that doesn't, and generally speaking, we think that the more edges you add, the more chance that there is a Hamiltonian cycle. And okay, here we just made that kind of precise, right? So G has no Hamiltonian cycle. That's the definition of G. It's one of the graphs of this set of graphs that have no Hamiltonian cycle, despite meeting the condition. And then we say that, of course, the complete graph with n vertices has a Hamiltonian cycle. So our graph G that doesn't have a Hamiltonian cycle is not a complete graph. If it's not complete, then there must be some edges missing. So I choose arbitrarily two edges, and I call them W1 and Wn. And I picked two vertices, W1 and Wn, in G that are not adjacent. So there is no edge W1, Wn, and of course there must be at least one edge missing because this graph G is not complete, because the complete graph has a Hamiltonian cycle, but our graph G does not. And I then make this new graph G prime, and G prime is just like G, but I add the W1, Wn edge. And now we see that this graph G has n vertices, because I didn't change the number of vertices, I simply added an edge. And of course, the degree of every vertex in that graph, already in G, the degree of every vertex met this condition. Well, here I just add one edge, so that's going to add 1 to the degree of W1 and 1 to the degree of W2, so it's certainly still going to meet this condition. In fact, the degrees of 2 of the vertices go up by 1. Therefore, so G prime meets this condition, but then G prime has more edges than G. By the definition of G, G is the biggest graph, biggest by the most number of edges, which is in that set. And so, if G prime, since G prime has more edges than G, then G prime is not in this set. That's just clear. This is the sort of move of positing this graph. This is the entire point of positing this graph G with the most number of edges that still doesn't have a Hamiltonian cycle. It's the biggest graph in this set S sub n. So if you add one more edge, then the new graph G prime is not in this set. But if G prime is not in this set, and yet G prime does have n vertices and does meet the condition, then the only thing that would be keeping it out of this set is that there's no Hamiltonian cycle. Or sorry, that there is a Hamiltonian cycle. So G prime has a Hamiltonian cycle, but G doesn't. In other words, just by adding this edge W1, Wn, I take my graph G, which doesn't have a Hamiltonian cycle, and I create a graph G prime, which does. And then, this is all just recapping the proof, I take a look, finally, at this graph G prime. What is this graph G prime? It's some graph which has n vertices. Here I've depicted n as being 7, just to pick a simple case to build some intuition. And it must have a Hamiltonian cycle, because it has one more edge than the biggest graph that doesn't have a Hamiltonian cycle yet. The other thing we said is that this Hamiltonian cycle in G prime must, in fact, use the W1, Wn edge. Because if this Hamiltonian cycle in G prime didn't use the W1, Wn edge, then the cycle would consist of only edges that were already in G, which is to say that G would have a Hamiltonian cycle. But G does not have a Hamiltonian cycle. And so if you have a graph that doesn't have a Hamiltonian cycle, and yet you add one edge and suddenly the graph does have a Hamiltonian cycle, then that Hamiltonian cycle must, in fact, go through the edge that was just added. I think that's pretty clear. So I have a Hamiltonian cycle. It doesn't matter where you start the cycle. Cycles are sort of, you can just circularly permutate it in any way. So we might as well consider it as starting at W1. It actually doesn't matter. But goes from W1 to W2 to W3 all the way around, and we finally get to Wn and back to W1. So what's built into this Hamiltonian cycle is that we do use, in a crucial way, this edge that we added, this Wn, W1 edge. And I hereby define W2, W3, W4, W5, W6, etc. as the vertices in the Hamiltonian cycle in G prime. In other words, G prime has a Hamiltonian cycle. If there's a Hamiltonian cycle, it must go through every single vertex. So it must go through vertex W1. And since the Hamiltonian cycle goes through vertex W1, then from W1, we have to have a next vertex. And okay, you could go sort of backwards to Wn, as we've said that edge must be in the cycle, or you could go forwards. So basically let W2 be the name of the vertex, which is the vertex visited after W1 in this Hamiltonian cycle in G prime. Let W3 be the vertex visited after W2 in the Hamiltonian cycle that exists in G prime, etc., etc. Okay, finally we get to the heart of the entire argument, and in period 9, I just was more careful to write very small, and therefore I fit this all in. Okay, I got some people to help me, but I don't like what they did, so I'm going to erase their help right now. But basically, by considering only a graph with 7 vertices, I managed to split this up into 4 possible cases. And maybe I don't want to call them cases. They're something. They're 4 possible somethings. There are 4 possible ways in which we could, there are 4 possible ways in which, okay, I should back up for a second and say that, of course, G does not, we're back to G now, it does not contain the W1, Wn edge. In fact, we introduced W1 and Wn as 2 vertices that did not share, that were not adjacent in G. So since there's no W1, Wn edge in G, then this is just the picture from the previous slide, but now missing this edge that I said was crucial. And G, of course, doesn't have a Hamiltonian cycle. Well, if G doesn't have a Hamiltonian cycle, and this W1, Wn edge is missing, but what do I know? What I do know, this could have been potentially more clear in class, what I do know for sure is that there's a W1, W2 edge. Why? Because W2 and W1 must be adjacent because the Hamiltonian cycle in G prime, went through W1, W2. And G and G prime are almost identical. They differ only by the fact that G doesn't have an edge between W1 and Wn, and G prime does. Therefore, if the Hamiltonian cycle in G prime went through W1, W2, let me go back. Since the Hamiltonian cycle in G prime goes through W1, W2, W3, W4, W5, W6, all the way up to Wn, and then back to W1 in that order, then of course in G prime, W1 and W2 are adjacent. In other words, there is an edge between W1 and W2 in G prime. There is an edge between W2 and W3 in G prime, etc., etc. But of course, then that means that G also has these edges. Okay, therefore, I know that W1 and W2 have an edge between them, W2 and W3 have an edge between them, etc. This was what the picture looked like before I marked it up. And now I ask the question, could it be that there was an edge between W2 and Wn, and an edge between W3 and W1? And what we said is that no, it's impossible for both of those to be true. It's impossible for W2 and Wn to be friends and for W3 and W1 to be friends. Because if they both, if those 2 friendships both existed, if there were edges here, then it would be possible to construct a Hamiltonian cycle in G, which avoids using the W1, Wn friendship, which doesn't exist in G. Specifically, we go from W1 to W2, then we cut from W2 to Wn on the assumption that that edge exists, then to W6, then to W5, then to W4, then to W3, and then on the assumption that this W3, W1 edge exists, we get back to W1, and thus we've completed a Hamiltonian cycle, using only edges that are in G. In other words, that's a Hamiltonian cycle in G. And yet we know that G has no Hamiltonian cycle, and so this can't be. So therefore, and now I regret in class not taking the opportunity, though the real... I don't know what's going on here. Why is that being so weird? Okay. What do I know? No, that one was fine. Oh, man. That one was fine. All right, my thing is getting very strange. Oh my god. Okay. So this is and. So actually I should start sort of at line 2 because it is oh my god, my pen has just stopped working. It's very disturbing. It's really here. This first picture corresponds to line 2. In line 2, I said, could it be that W2 is friends with Wn and W3 is friends with W1? And the answer was no. And really, the connective, I can't believe that I'm a logic teacher and I spent all this time in the very beginning of this class teaching you propositional connectives, including NAND. And NAND is really the actual connective that I want to use here in line 2. What I want to say is that it can't be true that W2 is adjacent to Wn and that W3 is adjacent to W1. It was the assumption that both of those hold that led to a contradiction. And so in line 2, it's never mind all this one or the other, but not both. That was kind of misleading or something because, in fact, neither of those might be true. And so really, the connective that I was searching for here is NAND. It's not true that this and this. Okay, if it's not true that this and this, then if you're considering the edge between W2 and Wn and the edge between W3 and W1, then since those can't both be true, then either neither of them is true or exactly one of them is true. And so my conclusion, which I thought I still explained decently well, is that together, the edge between W2 and Wn and the edge between W3 and W1, only one of them at most can exist. So this line contributes 0 or 1 edges in G. In other words, okay, I think that's pretty clear. And then the second picture here said, could there be an edge between W3 and Wn and an edge between W4 and W1? And the answer was again no. Because if those friendships existed, then we could do this figure 8 and we could make a Hamiltonian cycle in G. But there is no Hamiltonian cycle in G. And therefore, the second picture here corresponds to line 3, in which we say, again, the NAND of these two statements, right? It can't be true. It's not true that these are both true. And so 0 or 1 edges are contributed. And then, this is kind of repetitive of what we did in class, maybe pretty well. But here we have someone else's handwriting because I asked someone else to get involved. If there was, what is now the assumption? That we now ask the question, could it be that W4 is friends with Wn and that W5 is friends with W1? And the answer is no, that can't be true. And why can that not be true? Because if it were true that there was this edge, and here this person has drawn this edge between Wn and W4, and between W5 and W1, well then again it would be possible to make this Hamiltonian cycle. You go from W1 to W2 to W3 to W4 to Wn to W6 to W5 to W1. And here the order was Jean. Okay, and so, I want to kind of finish this page since this is all stuff we did already. Then, again, this third picture corresponds with this line 4, that these two relationships contribute at most 1 edge. And finally, here, this person at least wrote it out, looks like with a mouse, that I can't even barely read that. And maybe there's even like a typo here. That if W5 were friends with Wn and W6 were friends with W1, then that would be a contradiction. Why? Because then you could again make this Hamiltonian cycle that went like this. It started at W1, it went to W2, then to W3, then to W4, then to W5, then from W5 to Wn on the assumption that that friendship exists, then from Wn to W6, of course, that friendship we already knew existed, and then from W6 to W1 on this assumption. So, okay, we have done these 4 cases, and these 4 cases all lead us to the conclusion, or I don't even want to call them cases because I didn't really set them up, but I observed these 4 facts. And these 4 facts are 4 things that kind of all can't be true. And so the 4th picture corresponds to line 5 here. Okay, and here's where it got a little bit confusing potentially, at least in period 8 it was especially rushed because the handwriting was bad, and period 9 it was rushed as well. Here, just from looking at lines 2, 3, 4, and 5, we seem to be considering vertices W2, W3, W4, and W5 and their relationship with Wn. And over here in the second column of lines 2, 3, 4, and 5, we are considering W3, W4, W5, and W6 and their friendships with W1. So we're almost all the way to looking at every single vertex and their relationship with Wn and W1. So now we complete the picture by observing that in graph G, W1 and Wn are not friends, and that W2 and W1 are. Therefore, this line 1, if you consider these 2 edges, there's not an edge here. There's not an edge here, but there is an edge here. So precisely 1 edge is contributed by this line 1. In line 6, this is all repetitive of what we did in class. In line 6, there is an edge between W6 and Wn, because once again, that was part of the original Hamiltonian cycle in G'. And there is not an edge between Wn and W1. You see what I'm doing? I'm just incrementing this list here that's ending up in this yellow rectangle. W1, W2, W3, W4, W5, W6. And here, W2, W3, W4, W5, W6, Wn, which is really W7. Okay, so that line 6, contributes exactly 1 edge. And line 7, once you increment up, you get Wn, R, Wn. Well, that's just false because the graph is simple, so there's no loop between that vertex and itself. And here, when you increment past Wn, in a cyclic manner, you get back to W1. And also, there's no edge between W1 and W1 because there's no loop there because the graph is simple. This line, therefore, this line 6 is contributing exactly 1 edge. And this line 7 is contributing 0 edges. Therefore, what have we really done in some kind of weird roundabout way is we've made a list of every single vertex in the graph and whether or not they have an edge with Wn or not. And since every single vertex in the entire graph, including Wn itself, appears here, if I add up the number of edges appearing in this yellow column, then I just get the degree of Wn by definition. The degree of Wn is the number of edges incident with W1, and since it's a simple graph, it's just the number of vertices, that have edges with Wn. And similarly here in this green column, we've listed, as it turns out, every single vertex and its relationship with W1. So if I were to add up the number of edges in this green column, then I get the degree of W1. But on the other hand, because of this NAND relationship, line 1 contributes 1 edge, lines 2 through 5 contribute 0 or 1 edges, and line 6 contributes exactly 1 edge, and line 7 contributes no edges. So, keeping in mind that n is 7 in this case, we get 1, 2, 3, 4, 5, 6. Therefore, the sum of all, there are sort of like 14 possible relationships here, and precisely 4 of them we know to be false, precisely 2 of them we know to be true, and the other 8 are either true or false, but in any given line, only 1 at most can be true. And therefore, when you add up the total number of edges, you get that this is a number which is less than n. And so the last thing we did before the bell rang was to conclude this. The entire conclusion of this argument is that the degree of W1 plus the degree of Wn, remember that's what I got by adding all the edges in this yellow column and all the edges in this green column, in fact must be less than n. But that is a contradiction, because the degree of W1, by the assumption of the theorem, is greater than or equal to n over 2, and the degree of Wn is also greater than or equal to n over 2. And so, my God, the sum of the degrees of these vertices is greater than or equal to n. Okay, I've been talking for 25 minutes, and all I did was summarize everything that happened in class, maybe like 10% better. And so I condensed the 45-minute discussion in class to 25 minutes or something like that. Congratulations, me. What I wanted to do actually was something new. And, okay, the new thing, which is what you'll find in Gosset as well, is now the actual rigorous proof. The understanding all happened in previous slides, but if you're the kind of person that wants to see this all out in total detail, then we shouldn't assume that our graph has 7 vertices. We should do it in general. So now here's the full sort of proof in the most abstract way. Although it's quite hard, I think it's quite hard to follow. But now it should be easy to follow because it's just one layer of abstraction past what we've been doing on the previous slides. And so what is this? This is a picture of the Hamiltonian cycle in G prime. So it's exactly as before. There's this edge W1, Wn, which we added to G. And the Hamiltonian cycle in G prime goes W1, W2, W3. But now instead of going on to W4, I introduced kind of like a dot, dot, dot thing. And now there's this vertex WK, WK plus 1, Wn minus 1, and Wn, and back to W1. So it's exactly the same as before. Okay, what's this? This is now G. So this is, I'm going to kind of put this in a box or something and not talk about this picture again. And we're really going to look at the reality, which is G. And the reality of G is that there is no W1, Wn edge. And now I'm going to repeat the entire argument from before. What I'm going to say is the following can't be true. It can't be true that WK is friends with Wn and WK plus 1 is friends with W1. Because if these two edges existed in G, then it would be possible to complete a Hamiltonian cycle in G as follows. Go from W1 to W2 to W3, etc., 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 until I get to WK. But if WK is adjacent to Wn, then I could go to Wn, go back to Wn minus 1, and now etc., 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 to WK plus 1, and back to W1. So like I said, it's really the exact same argument as before, but actually this argument is like more efficient because instead of having to do 4 cases, I just do 1 case, but it's also more difficult to follow because it's more abstract. Okay, great. How do I now proceed with this argument? So I'll just say that this situation is impossible. It's impossible for, it can't be true for a pair of vertices, WK and WK plus 1, defined to be, remember, what is the definition of WK and WK plus 1? Just by even referring to WK and WK plus 1, what I mean by that is that in the Hamiltonian cycle in G prime, there was a vertex WK in that Hamiltonian cycle, and WK plus 1 was the vertex visited after WK in that Hamiltonian cycle in G prime. And so what can't be true is for WK to have an edge with Wn and for WK plus 1 to have an edge with W1. That is impossible. And so I hereby define the following sets. Let there be a set B. This is now finally, we're getting at the 29-minute mark. We're doing something new now. What is B? Let B be the set of all vertices in the, in V, the set of vertices in G, such that there is an edge between Wi and Wn. In other words, it's the set of vertices adjacent to Wn. I fear that if there is a vertex that is adjacent to Wn, that we will have one half of something that will lead to a contradiction. Okay, good. And let's define a new set, F. I have no idea what these letters, significance of these letters. They just came from gossip. Let this be the set of all vertices. And here comes this extremely kind of awkward definition that's very hard to understand. Call a vertex Wi in set F if the next vertex, if Wi plus sub I plus 1, W1 is an edge in E. In other words, categorize a particular vertex by whether not, in set F, we characterize a vertex by whether or not it's adjacent to Wn. But in set F, we characterize a vertex by whether or not the next vertex in the Hamiltonian cycle in G prime is adjacent to W1. And the big idea here is if you are some vertex, given some vertex Wk, you can't be in both of these sets. That's the whole point of this, right? You can't, if you're some vertex, you can't be in B and also F. In other words, B intersect F is in fact empty. Why? Because if you were some vertex Wk that was in B and F, it means that you are friends with Wn, and the next vertex in the Hamiltonian cycle in G prime is in fact adjacent to W1. But if those two things were true, then there would be a Hamiltonian cycle in G, and there isn't. Okay, so this is the key idea. Okay, but then it's also true, of course, that this set B simply is the set of all vertices which are adjacent to Wn. In other words, the size of B is just the degree of vertex Wn. And the size of F is just the degree of W1. Because after all, what is F? It's the set of all, actually this is a little bit more subtle, it's the set of all vertices such that the next vertex is adjacent to W1. But I mean, basically, there are, W1 is a vertex. There are a certain number of, it has a certain degree. That degree is the number of edges which are incident with W1. And for every edge incident with W1, there's a vertex on the other side of that edge. And that vertex will exist somewhere in this Hamiltonian cycle in G prime. And so the previous vertex, therefore, gets dropped into this set F. Therefore, the size of the set F is simply, the number of edges incident with W1. In other words, it's just the degree of W1. I think that's clear. Okay, and now, what? Is there anything left to say? Maybe there is something left to say because, oh yeah. And then, and then two more observations. What's the best order to do this in? Of course, maybe I'll start and then I'll decide what the next thing to say is. So now we say, all right, what about all the vertices that are in either B or F? Oh, I see. Okay, there's a particular vertex which is not in either one of these sets. I think it's worth it to mention this now. So note, the first note is that Wn is itself not in set B. Why is that true? Because what is set B? It's the set of vertices adjacent to Wn. But of course, this is a simple graph, so Wn is not adjacent to itself. Wn is not in set B. Fact. And the reason is because there is no Wn edge, because the graph is simple. Okay, but also note that Wn is not in F. Why is Wn not in F? Well, because what would it mean for Wn to be in F? Well, you're in F if okay, wait. You're in F if the next vertex in the Hamiltonian cycle in G prime is adjacent with W1. But what is Wn plus 1? This is because Wn plus 1 is in fact just W1, right? In other words, that's how we should interpret this, because it's a cycle, right? If you increment past n, you get back to the beginning again, right? Wn plus 1 should be thought of as like the next vertex after n. The next vertex after n is W1 in the original Hamiltonian cycle, which is what gave all these vertices their definitions in the first place. So, of course, there is no W1 edge, W1 edge, because, again, the graph is simple. Another way of putting, well, okay, I'll leave it at that. So therefore, if this vertex Wn is not by definition in B or F, then what can I say about the size of B union F? Well, B is a set of vertices of this graph. F is a set of vertices of this graph. So if I take all the vertices that are in set B and all the vertices that are in set F, and I put them all together, how many vertices could I have at most? Well, the most you could have is all the vertices. That would be n. But in fact, this vertex Wn cannot be in B or F. And if this vertex cannot be in B or F, then the size of B union F is in fact less than n. And here we go. Take the size of B union F and apply a simple inclusion-exclusion. It's B plus F minus B intersect F. But of course, what is the size of B? We've said it's the degree of Wn. What is the size of F? It's the degree of W1. And what is the size of B intersect F? It's 0. And all of this we now conclude by this discussion here is in fact less than n. So this is less than n, and this is less than n. Therefore, this is simply the generalization of the argument from the previous slide. I now put it in a box. The degree of Wn plus the degree of W1 has to be less than n. But that is a contradiction. Why is that a contradiction? Because G meets the condition of this theorem, which is that every vertex is friends with at least half of the other vertices. And so now it's just this exact argument from this other slide, right? The degree of W1 has to be greater than or equal to n over 2. The degree of Wn has to be greater than or equal to n over 2. And if you add these two equations, you get that the degree of W1 plus the degree of Wn has to be greater than or equal to n. And yet, we've showed that the degree of W1 plus the degree of Wn is less than n. So this contradicts the fact that G has this condition. Okay, therefore, we have a contradiction. And the contradiction is just that this graph G exists. What is graph G? It's the largest, but judged by edges, graph in this set S sub n. And since this graph S sub n is a finite set of graphs, it has to have a largest one. Well, if that largest one just simply doesn't exist, then in fact there are just no graphs at all in this set. And if there are no graphs at all in this set, then it's impossible to have a graph that meets this condition and yet doesn't have a Hamiltonian cycle. Thus, every graph that does meet this condition does have a Hamiltonian cycle, and that completes the theorem. What happened in this video that didn't happen in class? Really not that much. Just really this final slide, which simply proves the general case, and I think more elegantly, but also I would find this, if I were a student, a lot more difficult to understand on the first pass through, because there's sort of very strange, initially at least, construction of these sets, sort of B and F. But I think everyone gets it now. All right, if you paid attention in class and understood everything, and you watched this video, you now have a very good understanding of this theorem. I don't know if this theorem is really objectively actually all that important. You could easily take imagine a class on graph theory that never proved this theorem. This is not really like important in any kind of way. We're not going to build on it, but it is a nice attempt to describe some features of graphs with Hamiltonian cycles, which are so-called Hamiltonian graphs. There's no characterizing condition, but this is a sufficient condition. Okay, goodbye. Was it like an hour or something? No, 40 minutes. Woo! Goodbye.